Hey, how's it going? I'm checking our connection. It says it's excellent, but I just want to make sure sound and video is working. Cool, now I'm just not talking to myself in my office like a crazy person. I'm actually recording something. All right, thanks so much for yesterday doing some science with me, some real like engineering science, looking at paper airplane instructions, and then we went through, tried these instructions, and then started measuring how long it takes to actually make this paper airplane. And some of the things that we figured out was like, one, these instructions really need some images in them that would help in trying to say like, all right, here's how to do it, and this is what we're looking for. Oh, not that one. I was looking for our customer wait time. So in our made up business, we're folding paper airplanes for customers, and we had all kind of 15 of us folding these paper airplanes. So I recorded both the two-handed times for reported two-handed, how long it took us to fold those paper airplanes, and then also trying again with a one-handed folding paper airplane. So I'm taking this data and we're just going to take a look at it in a Google Colab sheet so that we can start running some analysis. So I took all this, I did some processing of that data and brought it over here. Let's get this, make it big. Here we go. So I have the time for two-hand, and I entered this all in seconds. So let's write that out in seconds. Seconds to make a paper airplane with two hands. Let's do this actually. We want to add a text. Recorded times are entered into the time to hands array. There we go. Let's say time to make a paper airplane with two hands, and now we can add another text here. And I'll copy all that, paste it in there with one hand time one. Just a little typo, because it's time two hand, time one hand, not time two hands, time one hands. And we can grab this too. Might as well add a comment, right? And so the next things that I'm going to do is process this data to try to turn it into like a cumulative density plot. So at least the way that I'm thinking about this is kind of like a serial processing. Like maybe we have one person folding paper airplanes and customers arriving at different intervals. So every time they finish a paper airplane, they start a new one. But the time that it takes them to finish that is going to be different each time. And that's what we found from our data, right? Like even though the same person was folding the paper airplane, it didn't create the same time. Different people had different times, and yeah, different people had different distributions of times. So what we have here is kind of like a cumulative, comparing like how long it took us to do it with two hands versus one hand. So some things that we can look at, like some of the things that are important. We can say np.mean time two-hand. Kind of nice. And we get that the mean time was about a minute, like slightly less than a minute. And what was the standard deviation? Those are kind of the two big ones. So 1 minute plus or minus 28 seconds. So call it 30 seconds. 1 minute plus or minus 30 seconds. If we're just going to use like 2 sig figs, which is kind of what I did here. For the most part, we always had like down to the second. So 58.6 is not, the 0.6 doesn't really help us. So about a minute plus or minus half a minute. Now let's look at the one hand. NP dot mean of time one hand. And you can hit tab, if it's offering you something, you can hit tab. So now with one hand, we're 1 full standard deviation above. So here we had 60, now I've got 95. So at least 30 seconds slower, or 30 seconds more time to do this. And I'll do std and 1, but still about the same standard deviation. So like roughly, and again, like roughly, with 1 sig fig, plus or minus 30 seconds. So here's the process that I'm using to like turn that into, rather than just using this data itself and saying that we only assembled this many airplanes, if I have a mean and I have a standard deviation, and I want to assume that this is a normally distributed data set, then I can create my own distributions from that. So that's what I'm going to do next, and I'll share this whole thing. This will be part of it. So first, let's just look at like a histogram of like what does this data actually look like. And I think, can I? No, can't do that. So let's grab this, and we'll just look at, for a two-hand, like what does it look like with two hands? 20% of our data is less than 40 seconds. There's another, or wait, 20%? Yeah, so, or no, 0.02, density true. So not 20%, 2%. 2% of our data was kind of that like 30 to 40 seconds. 1% was around like 40 to 50 seconds. We had a little more than 3% of our data. So I'm looking over here at these numbers just to get a sense of like what am I going to get out of this. So I would put, and our mean is right here at the mode. And that's a good sign to say that we have a normal distribution if your mean and your mode are the same value. And it kind of makes sense that we have some kind of normal distribution, because usually normally distributed data are due to a factor of a lot of random variables. So what you were paying attention to, if you got distracted while you were making it, if the paper was not the same, like differences in the paper as you're folding it, all sorts of things. But they all stack up into like something that's kind of normally distributed. And then, yeah, then over here, and we can even look at the one hand, and I'm keeping blue is going to be two hand, red is one hand. And now on the one hand, not on the one hand, for the one hand data, now we actually have something that's a little different. Huh. It doesn't look like normally distributed data, but I don't know. Because now the 90 seconds it's almost like bimodal now, right? Like we have stuff happening over here, stuff happening over there. But that's okay. It's data, and if the first one was normal distribution, probably the next one normal, but maybe there's something else going on. So maybe we need some other way of representing this. But we're going to take this and say, let's assume that it's a normal distribution. Then I'll generate random numbers for as many builds as I want to consider. So here I'll say that there are 1,000 builds. So we're going to build 1,000 paper airplanes. And this is not saying that someone's just going to sit down for the next 60,000 seconds or the next 1,000 minutes. How long is 1,000 minutes? 1,000 divided by 60. So someone's not going to sit there for 17 hours folding paper airplanes, but over 2 8-hour days, the time we're just going to assume that 8 a.m. the 9 to 5 paper folding is just, or even like with a lunch break. So, but anyway, so time is just ticking on. So what I'll say is that the build time is going to be, usually on average, we'll just have like, we'll start at time 1 and keep going time 2, 3, 4, 5, and multiply that by the average time. So that, and what this is doing is kind of like putting a number on the clock of like how many seconds have passed since the first build. So build 1 was at time 1, like 60 seconds, that's when it finished. Build 2 is going to be about 120 seconds. And then what I'm doing is adding a standard deviation to that and saying like, hey, build 1, maybe it took 40 seconds or maybe it took 80 seconds. Like that's all within our standard deviation. So that's what this plus equal sign is doing. Let's zoom in a little. So plus equal is just adding, so taking the build time with 2 hands and saying it happens on average every 60 seconds, but then adding either plus or minus, because the location is 0 and the scale is my standard deviation. So plus or minus that 30 seconds, or even up to, it could be up to like 3 standard deviations. So we might end up with negative times, but I sort those so that the build time, if build time 1 is 60 seconds and build time 2 is 55 seconds, we just switch them and say that the next one took about 5 seconds to build. Okay, and then we're going to take what is the difference between those build times 2, build time 2. So that NP diff is going to tell us how long it took to build each paper airplane. And this is just some stuff to like density plot, just makes it scales it so we can put them on the same scale as the data. And then increase the line width, make it colored blue so it matches the same color as our data. So we're plotting the 2-hand data and the 2-hand model. And then going through and doing the same thing for the number 1. So here I have the mean times the number of, this should say number of builds, right? N builds, sorry about that, because I renamed some stuff. So this should say N BUILDS, and this should say BUILDS, and you'll have the updated one, but I just BUILDS and BUILDS. All right, so that data that I was just taking a look at are these red and blue plots. They're not as, I mean, it's important, but that's kind of like just a quick snapshot of what would happen if we measured 1,000 different paper, rather than sitting down and actually having 1,000 folded paper airplanes. Now we have a difference, like here's my blue curve to say this is how long it took for all these 1,000 builds, some of them were almost 0 seconds, like 0 to something seconds, and then it could take up to 150 seconds, so a little over 2 minutes. Like if one finished early and the next one finished really late, how long would it take there? Okay, so then there's that. And now I'm going to create, so I'm using this histogram to kind of sort things into bins, and then this cumulative sum to get that cumulative density function. So it's basically taking like an integral of the histogram. So this is the histogram here, but I'm going to create a new one and save the count and bin counts, and then integrate over that so that I can look at what does that cumulative density function look like for build time 2 and build time 1. And I'll take 50 bins just because I have 1,000 different things there. And now I can look at 100% of my two-handed planes were built in less than 100, let's call it 170 seconds in that in the 1,000 builds, right? So over 1,000 different builds, 100% is definitely less than 200 seconds. And then meanwhile, my one-handed model is adding, now it's more like 200 seconds that I can't say for sure that it won't take 200 seconds for a plane to be built. And then if we come down here on average, what the difference was, here it's again like 60 seconds. It's just the mean of what we measured. And then over here, it's 90 seconds. So there's that 30-second gap between the two. And just some data analysis and kind of talking through like what do these plots actually mean. And then down on the lower end, this is saying like only 20% of our planes can actually get built in 30 seconds with two hands. Meanwhile, 20% of the planes with one hand could be built still about a minute. Like it'll still take about 60 seconds even for the fastest 20% of these planes that we're trying to build and deliver to customers. So, I mean, really, it's only a 30-second difference. So if you have, and this is where you have to be careful about how you present your data and what data you're measuring and what you're presenting. Because really, what I could say is that now, if everyone can build with one hand and it only takes 30 seconds extra, and this is the only data that I'm presenting, like I didn't show pictures, like really I should have pictures of a one-handed plane versus a two-handed plane. But as management, you could look at this and say, well, it's only a 30-second deficit, but people have two hands. So I could tell everyone, you have to fold two paper airplanes at one time so that now both of them, although you're building both of them slower, it's only 30 seconds slower. So now you're getting like, however the math works out, like 150% speed boost or like efficiency boost, because now you're getting two planes in the time that it took to build 1.5 planes. It's like, but we really don't want our technicians using two hands to do that. Or maybe they would say, like, since you can build with one hand, then maybe fill out paperwork with the other one. Anyway, be careful with how you present the data. But I thought this was really cool to go through and see this data and kind of play around with it in different ways. It's all entered up here into NumPy arrays. So if you have a different way of thinking about this or you want to approach it differently, go for it. The main things for if you want to get this data into this homework 5 project is you need the average part time here and then that standard deviation. And those are the two main things. So here I can plug in that standard deviation here and then the average part-time there. And that's how you can create this new time between plots. And I think this one we might have to sort it the same way that I just did. Oh. It helps to coming down here. It helps to run this step of saying like, hey, sort, make sure that there's never a negative time, because it just doesn't make sense to like go back in time because one took long and one was short. So if you run that and then do this and then do the rest of the thing, that would be better. And yeah, if you're here, everything is recorded in minutes, so just make sure the units kind of work out. Cool. All right, so that's all I had for today. Thanks again for your work and building all the paper airplanes, getting us some real data to use, and I will catch you next time. All right, thanks.